Hi guys, Godwin here. We're back for part 2 of the Lagrangian series. In the first part, we derived the Euler-Lagrange equation from the Hamilton's principle, which Sir just provided for us. And so we're gonna test it. We're gonna test out this magical equation for 3 cases, one of which is a spring. So that's the first one we're gonna do. The next one is a pendulum, and then the third one is a spring and pendulum. So we'll just see later. So for number 1, let's consider this diagram. Ooh, horrible start. You know what? Okay, yeah, fine. Yan. Okay. Yan. All right. So assuming we have this object right here with a mass of m, and this spring right here has a stiffness value of k. And then this is its This is its equilibrium position. Okay, so let's make it x equals 0, right? And then our positive x-axis will go in the direction of the right. And then sabihin natin that the thing has gone here. The distance that we have here is supposed to be x, right? Okay, just so we're clear with that. So we're going to use the Euler-Lagrange equation. We're going to find out first what the kinetic and potential energy is, and then we're going to substitute the derivatives and whatnot into yung Euler-Lagrange equation natin. So just so we're clear, we're not adding anything. We're not adding any forces. We're not removing any forces. So this QI here should be 0, and in fact, it's going to be 0 for the next 2 cases, but just so we're clear with that. So ayan, what will our generalized coordinate be for this case? So hindi naman siya nagmo-move like up or down, right? It only moves from left to right. That's what it's constrained to do. So of course, intuitively, our generalized coordinate should just be our x. All right. So let's formulate ulit yung kinetic and potential energies natin. First off, let's tackle kinetic energy, which of course is just always 1/2 mv squared. But from our last video nga, we discussed that this velocity here is just a time derivative of our position. So let me just rewrite this as 1/2 mass times x dot squared. So x dot, that's just the time derivative of position, right? So this is our t. And now for our v is just, since it's just rolling on the ground, it's not changing height, wala tayong mgh, right? Let's assume that this is z equals 0. So at this point, wala tayong height. So mgh, our h is 0, so that's 0, right? But another source of potential energy here is the force that makes the spring want to come back to equilibrium. That's called the restoring force. And that's the force pala, that's the force. What's the energy? So our restoring force, Fk, that's supposed to be kx. If we, if we derive both these, not like that. If we derive these, if we derive this equation pala on both sides with respect to position, we're going to have the work, right? Work, which is just the same with energy, which is just the same with potential energy. This is just 1/2 kx squared. And this is also explained further in the book. So I'm sure you're familiar already with this formula if you've gone through, where was this featured again? I think Kaling 2 or 3. Pero basta the one with the springs. Yeah, we've already come up with this equation before. And so, ang gagawin naman natin, we're going to put them into the Euler-Lagrange equation. So first, let's start off with what partial of t over partial of qi dot is. What is qi dot? That is just x dot, right? And so if we're going to treat our x dot as a variable, it's squared. So ibababa natin yung 2. It's gonna cancel with a 1/2. So we're left with mx dot, and then we're gonna derive it. So dot. Sorry. No, never mind, sorry. Later pa yun. Ooh, spoiler. Okay, we're just gonna be left with this with this expression mx dot, right? And so for this next term naman, the partial of t with respect to qi, so that's going to be our partial of t with respect to x. Wala namang x, so this is 0. And then finally we have partial of v with respect, oops, let's make that v, yeah, with respect to qi, which is just the same as partial of v with respect to x. And so this is the same thing as yung 1/2 mv squared, but it's now in the form of 1/2 kx squared. So x is squared, you're gonna move the 2 down, 1/2 times 2 is 1, so you're gonna be left with kx. And so let's plug all of this in na. So this is what I was mentioning. I got ahead of myself. What is the time derivative of the partial t over partial qi dot? That's our qi dot is mx dot. So this is now going to become mx dot dot, since it's now a time derivative of position. So double dot. So mx double dot minus 0, of course, and then plus kx is 0. And of course, this is our very loved spring equation. We can transform this into x double dot plus k over m x plus 0. And we can further transform that into x double dot plus the natural frequency squared x is equal to 0. So ayan, that's how we got yung spring equation just from the Euler-Lagrange equation, which is pretty magical. So our omega n here is the square root of k over m. Oh, just take note of that, take note of that. So number 2, we now have a pendulum. Oh dear. Okay, so let's let this be our equilibrium position. And then let's let this be a straight line. Imagine na lang na straight line. And let's imagine this to be a small enough value of theta. All right, so I actually spoiled what I was going to ask now. What is our generalized coordinate? So, yun nga, sabi ko in my previous video, or was that my take 1? Whatever. My intuitive sense for naming the coordinates in a pendulum is, of course, position. Where is this bob right here? Oh, I forgot. Where is this bob right here with a mass of m, the length of this is L, and then, of course, gravity is pulling down on it, which is G. Right? Okay, just so we're clear with that. Where is this bob in terms of x and y, right? So you might be tempted to say, oh, this is the x-axis, and then since it travels like downwards, maybe this can be the y-axis. But those are 2 coordinates. And the thing is, they're related with one another when you see that x squared plus y squared is equal to L squared, right? If you see this right triangle, and then it's all clear. So if you look at it from just like an outsider's perspective, how many degrees of freedom does a pendulum have? Of course, it only swings from like one direction to another, no? From left to right only. We're assuming this is all on the 2D plane, so no rotation on the 3D plane or something like that. It's just swinging back and forth from left to right. So it would only have 1 degree of freedom. Also, it's the same here, right? It's the same here with the spring. I can actually show if the viewers who are watching this is so redundant. Anyway, if the viewers here already know of the mobility equation or the Grubler-Kutzbach equation, I'm going to use version A. So we're going to account for the mobility of this configuration. So the Gruber-Kutzbach equation is just the degrees of freedom kapag unlinked yung mga link mo, number of links minus number of joints minus 1 plus all of the connectivities. Okay, so how many degrees of freedom do we have? Since this is 2D, this is 3 degrees of freedom. I'm sorry if this is if you don't understand this, in case you haven't been to machine elements yet, you can just skip. This isn't that important. The number of links here, one is the ground, and another one is the slider. So we have, we have 2 links minus, ano tawag dito, the number of joints we have is only one prismatic joint, which is the slider, right? That's 1 minus 1. So 2 minus 1 minus 1, that's 0. 0 times 3 is 0. Plus, what is the connectivity of the slider? That's 1. So the mobility of this machine here is 1. So it has 1 degree of freedom. Now for this one, we can ano tawag dito? We can compare it to just a hinge and then a link, right? So the mobility of that is, of course, this is still 2D, so that's 3 degrees of freedom. Number of links, one is the ground, one is the actual link, so we have 2 again. And then number of joints is just the hinge, right? 1 and then 1, so 2 minus 1 minus 1, 0 times 3, 0. Plus, what's the connectivity of the revolute joint or the hinge? That's 1 again. So this is still 1 degree of freedom. So that's a gut check to see if mas marami yung generalized coordinates mo kaysa yung degree of freedom mo, because they should be the same, right? And so a better way to to express where the position is in terms of our angle theta, because okay, let's draw this right let's draw this right triangle, and now we see that the x coordinate is just L sine theta, and then y is L cosine theta. What's great with using theta is that meron ka ng constant, which is the length of your pendulum. Unless it's not, of course, then don't use it. Anyway, ayun. We now have a better understanding for what the generalized coordinates are, right? So let's try finding now what the kinetic and potential energy is, right? So we have T equals 1/2 mv squared, but I just said we're not using positional coordinates, we're using rotational. So what's the rotational analog for this? Of course, it's 1/2 I omega squared. And so omega, of course, angular velocity, you can also translate that to I theta dot squared. So it's much like yung 1/2 mx dot squared, right? The only thing is this I now requires for us to compute for the moment of inertia of the pendulum bob. But it's pretty easy kasi we're treating it as a point mass, right? It's a particle, just one particle, 1 point in space with all the mass. And so that is just literally 1/2 m, and then the radius from the center of rotation to your actual point mass, which is, of course, the length of our pendulum, L squared. So it's gonna be, laki ng L, 1/2 ml squared theta dot squared. And so for, for, what do you call this? For potential energy, we're gonna have mgh. But what's our h? Okay, I'll set this at the lowest point. At the lowest point, my potential energy is my height is 0. And so what's this height? We'll call that our h. And then if we see, this is L. And then what's this height right here? This is just our y coordinate. What's our y coordinate? It's L cosine theta. So it's going to be mg and then L minus L cosine theta. Of course, we can remove this. We can make this mgl 1 minus cosine theta. And so we have theta dot and then theta. So it's now all in terms of theta. And then we can now plug this into our Euler-Lagrange equation. Okay, first we need the partial of t with respect to our qi dot, which is our theta dot, right? That's just the same as always. This is squared, so 2 times 1/2 is going to be ml squared, and then theta dot. And then let's just take the time derivative now. ml squared theta dot. Theta dot. So our theta dot is the time derivative of angle. So we're taking the time derivative of that. It's going to be ml squared theta double dot. Okay. And so yung partial of t with respect to qi naman natin, it's still going to be 0 because there's no theta term here. So we're done with what do you call this? We're done with kinetic energy. And now we're going to go, okay, we're going to go with potential energy now. Partial of E with respect to Qi. It's MGL. MGL is just a constant. So, titingnan na lang natin kung ano nasa loob nito. 1 minus cosine theta. Derivative of 1 is 0. And derivative of minus cosine is sine, positive sign. So this is going to be MGL sine theta. And if we put this all together, we're going to have ml squared theta double dot minus 0 plus mgl sine theta is equal to 0. So this is our famous pendulum equation. Of course, we can divide both sides by ml squared. We're going to get theta double dot is equal to g over L sine theta is equal to 0. And sabi ko, this is for, This is for small enough angles such that pwede na natin gawin yung infamous assumption na sine of theta is roughly just theta. So we can, we have a curve view. Yeah. So this is going to be theta double dot plus g over L theta. So this is now a linear, ordinary, second order differential equation. That's a lot of adjectives. And so this can also be counted as theta double dot plus natural frequency again. Not x. Who's copying the one above? Theta equals 0. And then we'll take note again that this is the natural frequency for this is g over L. Okay, now square root of g over L pala, sorry. Okay, now finally we have this chaotic system. We have, we have a wall and a ceiling, and then we have a pendulum bob that's swinging around. Actually, let's draw the the equilibrium point. Yan. That's too long. Okay, yan. The problem with this pendulum bob is that there's also a spring attached to the wall. So the spring has stiffness K, the bob has a mass M, the length of the pendulum is L, and then of course gravity is still acting on it, G. So how do we do this? Anong tawag dito? So let's just play with this in our minds. So if we drag this up, that's my hand. If we drag that up, okay, just draw it again. If we drag that up here, okay. We're gonna see that, we're gonna be intuitively informed that this spring is no longer straight left and right. It's gone up na because we pull the pendulum bob up, and it's not in the same region. It's not in the same plane of motion as yung spring natin in the first one, right? It can now move up or down because there's no ground anymore, right? And the path is constrained by the string of the pendulum, right? So we now have two choices for our generalized coordinate. We have this one, the x, and we have the theta. So, okay, you can already start seeing this, but we can only use one. We can only use one generalized coordinate. Why is that? So again, you're just gonna have to trust me that this is 1 degree of freedom for the people who aren't well versed in machine elements. But let's turn this into a linkage. Hello, it is I from the future, and I have realized the mistake. So I'm gonna come here to just do this again, the linkage again. Ah, man. Okay, let's do the linkage again. And then, sabi ko nga, the pendulum can be approximated for just the hinge. We're assuming that the pendulum wire is, of course, rigid because the angle is small enough para wala tayong distortion in the wire. And then I did say kanina na the spring can now move up and down because of the motion of the bob, right? It can now go higher and it can now go lower. It can't go lower, right? That the equilibrium position is there. So the spring can move up, right? Can move up or down. So let's just do this here again. Let's just try to be as exact as possible. And then, yeah, sige. Make it like this. Yeah. Okay. We're gonna count the links, which is where I made my mistake. So the ground is 1. This rope here is 2. And what I realized was there's supposed to be 2 links here, 3, and then 4. Because it can act like, imagine sliding your hands, sliding your arms pala, from each other. And that's essentially what a slider does. So that means there are 2 links here. So they're on the same, they're in a parallel plane of motion. Pero, they can only move coupled together, right? Because they are in the same, they're in parallel planes of motion. Yeah. So that's my mistake. I'm sorry. That took more editing time than it did. And then we'll count the number of hinges. This is number 1, number 2, number 3. There's a revolute hinge here, right? Because you can the bob can move from here to here, and the slider would be different now. Okay, it can permit motion. Boom. Okay, so there's 1, 2, 3, and then of course the slider is a joint. So we have 3 links. 3 degrees of freedom for 2D motion. We have 4 links. We have 4 joints minus 1. So this is going to be 4 minus 4, 0, minus 1, negative 1. So 3 times negative 1, that's going to be negative 3. But we're going to count the connectivity. Finally going to count the connectivity of all of the joints, which are 1, 1, 1, 1. So all of that is 4. So negative 3 plus 4. Finally we have the 1. Okay. I'm justified in making the decision that there should only be 1 generalized coordinate. Okay, there. Which one are we gonna use? So there's this relationship between theta and x, where your x is just what is this? Your x is just L of sine theta. So we can either make x in terms of theta, or we can make theta in terms of x, which is, it's the arc sine of x over L, which is not that good. So I guess we'll just use x equals L sine theta and make everything in terms of theta. So same as always, what's our kinetic energy? Well, here, isa lang object natin, which is the pendulum bob. It has a mass of m, and it has a velocity, translational velocity of v, right? Of x dot. Pero in this case, we're going to make it rotational because we're using theta. So it's going to be 1/2 I omega, so theta dot squared. So that's okay for that. For v, this is where it gets interesting because we now have 2 sources of potential energy. One, of course, is the height. So we'll make this z equals 0 again. And so let's just copy from this time. Nasan yung ano? Yan. This is just our one part of our potential energy, mgl, 1 minus cosine theta. Wala namang nag-iba dun sa setup ng, what do you call this? Ng pendulum. The only thing that's different now is that this spring is now stuck to is stuck to our pendulum bob. So we're going to add plus, what's the potential energy for a spring? That's 1/2 kx squared. But the problem here is kx squared, I thought we're using this in terms of theta. So we are mgl times 1 minus cosine theta plus 1/2 of k. So x is L sine theta. It's going to be L squared sine squared theta. All right. So let's derive t with respect to qi dot, which is our theta dot. This is just I theta dot. Right? Oh, right. Oh nga pala, I forgot to turn this into, that's why I was confused. Like, I don't remember this. This I is the same for the moment of inertia of the bob, which is just ml squared theta dot. Yeah, theta dot. Yeah, okay. And then if we give that a time derivative, that's just going to be qi dot. That's just going to be ml squared theta double dot. All right? And so, wala rin naman to, partial of t with respect to qi. That's nothing because walang theta term, right? The only thing we're going to have a hard time doing is this, the partial of potential energy with respect to our generalized coordinate. So it's going to be, we'll do this first, our mgl sine theta, which alam na natin from before, right? This one. But there's this thing, 1/2 kl squared sine squared theta. And so what's the derivative of sine squared theta with respect to theta? Well, let's just treat the sine theta as one thing. So it's something squared, right? If you're gonna derive something squared, bababa mo yung 2. So 1/2 times 2, that's also gone. So it's gonna be, why won't it delete? Yeah, kl squared, cancel yung 1/2 and 2, and then we give the thing, and then we multiply it by its derivative, right? Cosine theta. And now this is our equation for this term. And so we're going to combine all of this again into one big equation, ml squared theta double dot plus mgl, I'm going to skip this na, mgl sine theta plus kl squared sine theta cosine theta equals 0. And so we now have two approximations. We have sine of theta is near theta, and cosine theta, well, if the angle is small enough, it's near to 0. So it's near cosine 0, which is 1. So tanggal. And then this becomes theta. This becomes theta. And now, I actually shouldn't have done that since I'm gonna box it pa. Go. Do it, go. I don't know, my computer is pretty slow. Okay, there. Can box this. And then we can do the approximations. Go. Yeah. We can do ml squared theta double dot plus mgl theta plus kl squared theta again. Right? Since cosine is just 1, sine is just theta, sine is theta, 0. Okay, we have this thing. Okay, so this is getting interesting. We divide ml squared on both sides. We're gonna get theta double dot plus, let's just group these guys together, no, under 1 theta. Lahat sila merong common factor of L. So we're just gonna say mg plus kl over ml of theta is equal to 0. Right? So that's another thing. So now, what's our natural frequency? Our natural frequency is mg plus kl over ml. What's interesting about this, if I decompose this fraction, it's going to look like g over l plus K over M. This G over L is the pendulum. This K over M is a spring. So that's just very neat for me. Ayan, that's our three cases, all very easily done with the Euler-Lagrange equation. So I hope this two-part series has will help people try to understand the Lagrangian better than, not understanding. So yun, I hope you guys enjoy, and I hope you guys continue to learn, please. Let's do this all together. Thank you, guys.